who's likely to be here is here. I am, well, we are going to be looking at the last chapter, last part of chapter 11, estimating the difference between two means. Quite long, these questions, pretty much regurgitating in a slightly different form things that we've done in the past. And what we're going to be looking at is experiments or data collection where they're interested. Is there a difference between two groups? And in particular, is there a difference in the means between two groups? And this is essentially the technique we're going to do. We're going to do a confidence interval, and we're going to do basically use this formula. And it's the statistic is that bit there. The difference between the sample means, plus or minus the magic t-score. And this thing here is called the standard error. And it's the standard error of the difference x1 bar minus x2 bar. We need to know a couple of other things. When you do a difference between two means, the degrees of freedom can sometimes be a little bit harder to calculate. One of the methods that they use to calculate it, but actually it's not the only one, is that you look at these two numbers, the sample 1, how many people were in it, take away 1, and sample 2, take away 1. And whichever one of these is the smaller, that's your degrees of freedom. So if you had one sample with 50 and the other with 80, 49 would be the degrees of freedom. Right. The magic t-score comes from that table that we've used in the past. So let's create just a kind of starter story, and then we'll use some of the homework questions, I think, after that. Let's suppose that we are interested in two drugs. And this is quite a common thing that's done on. So we have the old drug, and we have the new drug. And let's say that what these drugs do is they increase, mix them up. They help to increase your iron level, right? So pregnant women, for instance, very often during pregnancy, they lose a lot of their iron and calcium and a few other things because the little growing babies use them up. And you might get a supplement, right, to just make sure that your iron levels don't go down too far. Because if I know a little bit medicine, which I don't, I believe iron is important to blood. Don't know why, but or even if that's true, but I believe it's true. So you take the old drug, and the increase in the iron was 32 units, and the standard deviation was 5. And the new group, they took that drug and they get 41, and the standard deviation was 10. And in the first group, it would be, say, 200. And in the second group, let's say it was just 100. What we're interested here is estimating the difference between the two. And from that, we can then make a judgment call of whether the new drug is doing a better job by increasing the iron level in the blood. Well, superficially, isn't the new drug doing better? Right. We're assuming you don't overdose on it, right? So it's in the safe levels. So it's better. Would you agree that the standard deviation is a lot? So if you take that new drug, for some people, it'll be a lot better than that, which is good. But for a few, won't it be a lot worse than that? So it might not be such a good drug on balance. Sample sizes are nice and healthy, so I'm feeling good about that. This would probably have been done as a double-blind experiment. So can you imagine that the pregnant mothers are under their own doctor's supervision, and they're doing a clinical trial, and they're getting a supplement, and there isn't really a placebo here, isn't there? An old drug and a new drug, rather than a placebo and a drug, right? But it's still double-blind, because the pregnant mother won't know if she's getting the new pill or the old pill, and the doctor doesn't know which medicine she's receiving. What the doctor will be doing is just watching after the mother and, taking blood samples and sending the iron levels back to the drug company. So let's put this package together. We got a lot of things to calculate. I guess I should calculate this fella, which is 32 take away 41, which I believe is -9. And it's okay to have negative numbers. And I also need to know degrees of freedom. And what do I know about the degrees of freedom? Well, it's either 199 or it's 99. Do you see that the choices are the smaller of these two? So are you happy about why I'm picking 99? Okay, so you look at both sample sizes and you subtract one from them, and that would be it. That's good. Well, I haven't decided what we're going to do, so let's do a 95% confidence interval. So in this case, I need to find that guy. Now, to save me going out and back in, you're just going to trust me what I'm doing here. I'm going to that table that we have online. And hopefully you've done that table enough times to feel comfortable with it. Just try to make it big enough to see. Right, there we go. My eyesight's not great, but that's it. So I'm going to 99 degrees of freedom, but there isn't any. So I'm going to use 100, right, because that's pretty close. And I'm going along the 100 row, and I'm looking for the 95er, and the guy I got was 1.98. Are we all pretty comfortable about getting this magic number? Because if you don't get the right number here, you're always going to be wrong, right? Your interval's not going to be the answer that WebDesign wants. Are we good at calculating or finding these guys? We feel good about it. Degrees of freedom, read along, take the number that's there. Okay, let's get started. The 95 percentage confidence interval is going to use this guy. The difference is -9. The magic t-score is 1.98, and I guess I probably should have done that earlier, but it's too late now. So it's going to be 5 squared over 200 plus 10 squared over 100. So I'm going to do this piece here, hopefully. 1.98 times the square root of 25 divided by 200 plus 100 divided by 100. I'll just put it in because it's a calculation. And I am coming up with, let's call that 2.1. So our interval could be anywhere between negative, is it 7? No, it's going to be, negative 6.9. There we go. I still can't count to save myself, sorry. Third time lucky. Negative 11.1. Good. To negative 6.9. Right, so we have a confidence interval that we believe the difference between the two treatments is somewhere between -11 and -7, very roughly. All those numbers are negative. Isn't that significant evidence for something? And is it evidence? Well, let's look at what it's telling us. Isn't it telling us that this is smaller than that? Or if you want to turn it in its head, isn't it saying this is bigger than that? So what would we conclude? We would conclude that there's significant evidence. It's always a good idea to put down, at the 95% level, or the 99% level, or the 90% level. Isn't it kind of helpful to know that number? Just gives you a feel for how much trust to put in. So significant evidence at the 95% level that the new drug, I'll call it is better, because we want it to be bigger, right? Is better than the old drug. So in a clinical trial, for instance, you could use that as evidence when you go to the FDA that it's worthwhile them allowing this drug to be used now with pregnant mothers. Now, new drugs go through an awful lot of hurdles, or at least they should. I believe they do. The first process that they do is normally a safety check. So they just do the drug and they see if there's any side effects, anything really bad happens, right? If people take it, even before they look at the efficacy of it, does it do any good? They look, does it do any bad, right? Does it make people worse? Does it cause blood clots? Who knows? And you never can be sure. Even the most innocuous drug in the world can have some really horrible side effects that you never even imagined were going to happen when they started with the drug. So if it goes by that hurdle, the FDA then has a second kind of level, and that is you have to prove that it's more effective than the drugs that they've got today. Normally the FDA don't allow a new drug on the market just because it's safe, because it could be safe and do a worse job than the medicine that's being used right now. That would be a bad idea. Would you agree? It'd be worse if you were giving stuff that didn't have any bad effects, but it wasn't very successful, right? You might as well give somebody a sugar pill and say, "Oh, that's going to help your iron level," right? It won't hurt you, but it won't help your iron level either. So it has to be proven that it's better. So that's what this would be. This would be the evidence that you would present to the FDA, and they would check that it's valid and was done correctly. And if you get by that hurdle, then you've basically got a small license to print money. Because and I don't know what the number is, I'll make up a number. For 10 years, you've got sole control over that drug, right? You produce that drug. And what happens then is that, and it has been known, that the pharmaceutical company try and push the new drug. Have you ever noticed lately how many adverts are on television telling you to talk to your doctor about taking drug A? Right. Is your blood pressure too high? Why don't you try this new drug called drug A? Or, blood thinners or whatever it might be. And the reason why they want you to do that is that, the new ones are much more expensive than the old ones. And so don't they want you to buy their drugs so they can make money? That's my little bit about drugs.
So I'm actually slightly confused by I thought if you got, and I don't understand. Okay, so I thought if you got both positive numbers, that meant that the new drug would be more successful. If there was an overlap of 0, then that meant inconclusive. And if it was both negatives, that meant that it wasn't successful.
Well, it depends on the order that I did it. Do you notice I did the order old and the new second?
So if you had just done new first?
Yeah, it would have been exactly what you said.
And it would have been positive numbers.
And it would have been positive.
Okay, got it.
Right. I mean, if I just labeled this X2 and I labeled all these X1, wouldn't the only difference to the calculation be this would be a positive number? Because wouldn't these be the same? They'd just be swapped places. And wouldn't this be the same? Right. So all of this would be the same. And wouldn't it just be, big takeaway, small, small takeaway, big? That's the difference. So when I went and said this is negative, that's evidence that this is smaller than that. And if the first one is smaller than the second, isn't it also true that the second one is bigger than the smallest, right? I'm bigger than my younger brother. My younger brother is smaller than me. It's the same piece of information described in 2 slightly different ways. Right. That help? Okay, so let's look at what these look like in the homework world. When you, and hopefully some of you will actually, do these types of things, I'm trying to close some windows here. As you can tell, I'm not good at multitasking. The information that you see very often is not very clean. So what I'm going to show you is our first one is question 1. And we'll show you what computer software, which pretty much does all of the number crunching for you. I don't know what this one is, but there's a couple of statistical packages. It could be SPSS, statistical packages for the social sciences. That's a very common one that's used by social scientists. You know, they collect data. They don't do any of this number crunching, right? They don't find SEs and they don't find margins of error. All they basically do is conduct the experiment, collect the data, and then actually they normally pay someone else to type the numbers into the computer. They don't even do that. But what they get back is something that looks like this. So in this particular story, since we're kind of collecting data, let's see if I make it a little bit bigger. Too much. Okay. They were looking at the testosterone levels of men in different professions. And the researcher suggested that there's occupational differences between the male testosterone levels. So I'm making this up. There's probably a really good chance, although I have no evidence whatsoever to prove this, that professional boxers probably have a very high testosterone level, and that kindergarten male teachers probably don't. I'm just thinking the profession you go into. It wouldn't be very good kindergarten teacher if you had the mindset of a professional boxer that wants to kill the other guy, right? I probably wouldn't work well, right? So I'm making that up, but you can imagine there could be differences, right? Different professions have different testosterone levels, and they're just interested in seeing if there is any significance in that. And the two groups that they looked at were medical doctors, which I'm sure MD is there, and university professors, which is, I guess, profs. And this basically has all the data. Can you see that they took 16 doctors and 10 professors, and that the mean testosterone levels were these two numbers, and that the standard deviations was this, and they collected some guys that were irrelevant to the story. And they calculated the difference, which if I do it in my head is 1.2. You know, I didn't need that, but the computer did it anyway. And the key is that guy there. You see that it's got the interval already created. Now, what's the difference between you and a social scientist who looked at that data is they would only really be interested in the final result and not all the working that got to it. But don't we know how these numbers actually came about? Because we've done them, right, by hand. And if you're wondering, why is he boring me stupid, getting me to do 20 examples of these, you're probably only going to get this opportunity to do them by hand. And I don't like magic in statistics. I don't like, oh, well, you just give these numbers to a computer and it tells you if it's right or wrong. Isn't it at least helpful to know what the process was and what you would have done if you had to do it by hand? So when these numbers come out, they have a little bit more reality to them. And so I could imagine doing this calculation from scratch, but it's nice that they gave me it. What's the conclusion on this interval? Is there any significant difference between these two groups?
No.
And correct. What's the reason? How do you know?
Because it covers 0.
There you go. So that one would not get published. Can you imagine somebody in a medical magazine or journal saying, yeah, we conducted this experiment and there's no statistical difference between these two groups? That's not very important or useful. Isn't it more important when you find differences, not when you don't? Because you could say, well, I've also done 400 other versions of this, and none of them had any statistical difference. Well, you might be saying to yourself, why are you spending all your time and effort doing something when you're not getting anything useful out of it? Except to say, you know, professions don't have a difference in testosterone level.
How come?
Now, Yes.
Question, is DF degrees of freedom? And if
Yeah,
so,
it's a funny number,
why is
22.
it
Do you see that?
22? Yeah.
Yeah. The one that we use is the smaller of the two. That's a kind of rule of thumb. If you want to look up the textbook, and they will show you a ridiculously ugly formula for calculating degrees of freedom. And no doubt the computer has that ugly formula plugged into itself. There are other ways to calculate degrees of freedom. Another way that I've seen is you add the two together and subtract 2. So you add the sample 1 plus sample 2 and subtract 2. I've seen ones where you add the two together and only subtract 1. I've never done the horrible formula, but I'm aware of it, where you plug in lots of things and the number 14.8 comes out and you call it 15. I suspect that they use the ugly formula. The thing is, it's kind of magic now, because I don't really know where the 22 came from, but I do know that the software generated it, so it had to have a reason. Which one of these guys here is the formula that you would use to get that guy?
The third one.
You recognize my general formula? That's that one. Now, it's saying here, can you identify the statistic, the standard error, and the multiplier? Right, the statistic, isn't that the difference between the two? So that's 1.2. If you're looking for the standard error, I don't think it's actually in here directly. But if you take that number and square it and divide it by that number and that number, basically, if you do that guy there, won't you get the number that she's going here? And the multiplier, what do you think they mean by the multiplier?
The t-score?
Yeah, the magic t-score. So when you have to go to your table and find out what is this one, the 95? Yeah, find what the 95 is for a 22 degrees of freedom. And that's no, well, maybe not. They then go on and they do interpret what a 95 means. And one of these guys is, since the interval contains 0, just like Cheyenne said, there's no significance in the data. But the main part of this question is, when you do this, if you ever do get to do experiments and collect data, you will use software. You will typically not do it by hand. Oh, one last thing. Now that I've looked at this data, why am I not even interested in the answer, even if it was statistically significant? What's wrong with this data?
Sample size?
Sample size. Don't we want about 30? I mean, as a bare minimum. So if I got a report from someone and I looked at that, the first thing I tend to do is look at sample size. That's one of the things I look at. And if I see it and it's too small, I'm going to say, well, that's interesting, but you haven't convinced me. Go and do it again, but do it with 50 people each, right? Give me a sample I can work with. Can you imagine 10 people in a sample? It wouldn't take too many large values or small values to shift that mean a lot. Would you agree? It could be quite easy to shift it. And you could then end up with, allegedly, a statistical significant result. So I'm always wary when I hear about someone saying, oh, there's been a new experiment and they've proved something. If they don't tell me things like, how many people were in your experiment, right? Did you do it with 20 people or did you do it with 2,000? If you do it with 2,000, I'm impressed. I'm ready to listen. If you do it with 20, I'm not bothered. I don't care what you tell me. You're not going to convince me one way or the other, right? Look at the confidence interval. Side issue here, but this has happened. I've seen it happen. It's totally It should be illegal. People, statisticians, should get arrested for doing this. I want you to imagine that I collected some data and I did the same analysis, but I did a 90, a 95, and a 99% confidence interval. And on the 99, the answer was -5 to +11. When I did a 95% one, it was -1 to 7. And when I did a 90, it was 1 to 5. Can you imagine that it is possible under certain circumstances that the intervals you get, they will be smaller, we know that, but can you also get an interval that had 0 becoming an interval that is all positive? Can you imagine if you shrink enough, that can happen? If I use this interval, wouldn't I say I have proven that there is a statistical significant difference between the two groups? Whereas if I use the 99% one, wouldn't my answer be there is no statistical evidence, right? We don't know. And the only difference is the confidence interval that I used. Can you see the temptation that people have to choose a confidence interval that gives them a statistically significant result? Who's going to be able to publish a paper in a medical journal that says the testosterone level isn't any, there's no evidence that there's a difference, right? Nobody's going to publish that, are they? But they might publish statistically significant result, even if it was based on a poor confidence interval. Second one, couldn't you get statistically significant results because both your samples were, say, tiny? You know, just by luck, can you get a few people really big in one group and a few people really small in the other, and that separated them? Is that truly real evidence, you know, that something's going on? No. So be on the lookout for confidence interval that was used and what sample sizes were being used, because they're the two sneaky ways that people who are unscrupulous tell you that the science is proving something. So when I hear them saying statistically significant, or the new jargon word is the science is proving it, you got to tell me how many people you got that data from. You got to tell me how you collected that data, because it could be biased. And you've got to tell me what kind of confidence interval you were using. After I know those things, then I'll make up my mind whether or not there's evidence there or not. Okay, let's move on. Got my little rant about, and it's not normally the statistician to blame. Do you know who's to blame? The people who want to hear the answer they want. Yeah. I don't know if this is true, but I've been told that sometimes they keep doing the experiment over and over and over again until they get a set of data that proves what they wanted. So they do 10 times and one of them says this is true, and they forget the 9 that failed and they keep the one that passes. That would be a bad news. Okay, next story then. This is similar to question 2. Volunteers who developed a cold within the last 24 hours were randomly assigned to take zinc or a placebo. Okay, it sounds like a double blind. The first group, the ones who took zinc, there were 23 participants, and the mean number of days that it took them to get over the cold was 7.2 days, and that their standard deviation was 1.6 days. The placebo group, how many were in that group? Oops, my apologies, that's 25. And this is 23, right? So 25 and 23. The ones who didn't get anything except a sugar pill, I apologize. my scanning is back and forward. I'll put the numbers in and I'll tell you who the guys are. Let's do it that way. The ones who took the placebo, there were 25 in that group, 7.2 days to recover, standard deviation 1.6. The second group, the ones who got zinc, 23 in that group, 4 days to recover, standard deviation 1.4. We are going to go through the entire process. They kind of break it into steps, so I'm going to show you what that would be. The first step is the statistic. So in this case, 7.2 take away 4.0, and the answer I come up with is 3.2. They also want the standard error. The standard error is this guy here. So it's this guy plus this guy. So it's going to be number 1, 1.6 squared over 25, 1.4 squared over 23. And I'll go here, and I'll see if I can come up with this fella. I got a 1.6 squared divided by 25 plus a 1. Jimmy, I picked up an extra 2 here. A 1.4 squared divided by 23, and I got a 0.433 out of that. And then part B, a 95% confidence interval. We are going to use degrees of freedom of 22. This guy -1. And that's going to give me this fella, right? Well, I'm going to zoom in, get that table, wherever it is hiding. Is it here? Oh, I've lost my table. Where has it gone? Oh, here it is. A 95 with 22 degrees of freedom is a 2.07. So we're ready to go. It's going to be the difference between the two plus the magic t-score and the standard error. The difference was 3.2 plus or minus 2.07, and the standard error was 0.433. So it ends up being 3.2, give or take 2.07 times 0.433. And I'm calling that 0. I don't know what accuracy is. Oh, let's just call it 0.9. It's pretty close. And that could be as low as 2.3, could be as high as 4.1. And so there's my 95% confidence interval. The way they want it to be written is from 2.3 to 4.1 days. So you write it like that. And then they go on and they do usual. Looking at that, would you agree it's statistically significant? They're all positive. Now, in the context of this, the placebo is bigger than the zinc, right? So people who take the placebo have the symptoms of the cold more than the other ones, right? So I would interpret that the other way around. if you take zinc, won't you have fewer days with the cold? That's essentially what it means, doesn't it? Okay. So evidently, according to this, it's statistically significant. I don't like the sample size, so I'm going to ignore it. But it doesn't mean that zinc isn't good. I've heard zinc is used quite frequently. Somebody tell me if I'm wrong here. I think I've read that zinc is good for the immune system in general. Anybody heard that? Right. So I'm sure there's good data out there where someone's done, 200 people, that kind of thing. So I'm throwing it out not because I don't believe that that's correct. I'm throwing it out because I don't like sample sizes that small. Once you've done enough of these types of stories, don't they basically just have a flow to them? They all kind of look the same after a while. So this is going to be my last version of this. And then we are finished estimating the difference between two means. And I guess I should maybe pick one of theirs. Okay, let's do a sexist one. Did you know that men's heads are bigger than women's heads? Allegedly. This is question 5. They collected a random sample of men, self-identified men, and there was 45 in that sample. And their head circumference was 57 centimeters. And the standard deviation was 2.3 centimeters. And then they got some self-identified women. And in the second sample, there was also 45. And the mean for the women is 54.6. And the standard deviation was 2 centimeters. Oh, I'm not doing a 95. They all seem to like 95% confidence intervals. I'm going to just pretend the question said 99. Let's do a 99 just to be different, right? So find a 99% confidence interval. So we're going to go through the entire process of getting this. Let's have a good look at the data before we go any further. At least it's bigger than 30. Do you agree? So I shouldn't really throw it out. No, I'd like it to be 450, but 45 will do. Would you agree that men's heads are bigger on average than the women, at least within the samples? Men have got a slightly more variation in how big their heads are. Do you think that's going to be a big enough difference to be statistically significant, or could that just happen with randomness? Do you think, what's your gut feeling? Are we going to get a statistically significant answer? Any gut feelings? Any gamblers? I'm going to say yes. I think there will be. And so I'm about to maybe get shot down in flames and find out there's not. We shall see. Okay, so I want to calculate the standard error. So it's this guy. And 2.3 squared over 45 plus 2 squared. Are they both 45? Oh, good. They are both 45. That's fine. So we have a square root of 2.3 squared divided by 45 plus 2 squared divided by 45, and I get about 0.45. And I'm going to get the difference. Which is what, 2.4. And I'm going to find the magic 99%. And the degrees of freedom this time are 44. So you just bear with me for a few moments. I'll go looking for that table. And a 99, 44. I don't have a 44, so I'm taking a 40. And a 99 on 40 is 2.7. So here's the guy that we're going to use. That fella plus or minus this guy times the standard error. And this guy is 2.4. This fella is 2.7. This fella is 0.45. Almost done. 2.7 times 0.45 is plus or minus 1.2. So the answer that we got was somewhere in the region 1.2 to 3.6. So there is, it's statistically significant that men's heads are on average larger than female heads. And it looks like the answer is somewhere between 1 and 3 centimeters circumference. I don't think that means too much that your head's bigger. Couldn't you have a big head and nothing inside it? So you could be pretty dumb with a big head, and you could be pretty intelligent with a small one. So I don't think I would be too worried about that. Any questions? Okay. Before you go, can I remind you, homework is coming up this Sunday, and your test will be on Tuesday because they're holiday on Monday.